Hi, and welcome back. This is video one of three on chapter 13. Now, chapter 13 introduces us to our first fundamental force, and it will be the only one that we talk about this semester. Next semester in University Physics 2, you'll see another called Coulomb force. Um, so, the force we're going to be talking about today is an important one. It was given to us, at least conceptually, by Isaac Newton, and we'll get to that later on. Um, and it's the law. It's the force of gravity. Now that said, what I'd like to do in this video is to give you a historical foundation as to why this was such a big deal. And to start off with, what I'd like to do is to discuss a different science briefly, and that's the science of astronomy. Now, astronomy is, for all intents and purposes, the study of the universe. That said, it's generally considered to be the oldest science that uses the scientific method. We'd say it's a modern science, and you'd say its inception point was probably somewhere around 400 to 500 BC. Now, that said, um, back then in early Greece, which is where astronomy was sort of thought up, um, the Greek did not understand that when they were looking at things in the sky, they were looking at it from our vantage point of going around the sun. So what they did was to take what they saw up in the sky and the motions of the heavens and take it as a literal view. So if you were to ignore or just forget everything that you know about astronomy right now and walk outside and say, okay, sky, tell me, where do I live? Well, you see the sun go across the sky, you know, once every 12 hours approximately, and then return in another 12 hours. You see, the stars appear to orbit around us once every year, which is a consequence of our motion around the sun. And you even see the planets sort of appear to go around us, and we're going to talk about what's going on there here in a moment. So everything tells you that you're at the center. So if you think of this, we'll say as being an orbit, if you were going to, as per the ancient Greek rather, put the Earth's place, it would be at the center like this. Now, this is actually an example of a cosmology. This is one of the earliest cosmologies that had been created. This one, I believe, was created by a guy named Thales of Miletus. And basically, in his model of the universe, he had the Earth at the center, like this. So here's the Earth, like that. And then between the Earth and the Sun, which would be somewhere around over here, we'll say, going around us. So sad sun because he's wrong. You'd have the moon. Now, why does the moon sit between us and the sun? Well, one of the things that the early Greek knew existed were eclipses. Specifically, what we would call a solar eclipse. There are other types of eclipses as well. There's another one where the Earth gets between the moon and the sun, which they knew about as well. And you can see the shadow of the Earth on the moon. So they knew that positionally, the moon had to sit somewhere between us and there. Now, the shapes of the orbits were circles, and this actually is true up until somewhere around 1600 A.D. As per this dating scheme. And the reason why they picked circles was because the Greek believed that the universe was an artifact; it was created. They also believed that mathematics was a perfect thing, since it was something that sort of sat up in the imagination and the consciousness. And since the universe was perfect and mathematics was perfect, math would be the perfect tool to describe nature, and a creator of some sort would choose the most perfect shape for the orbits of the planets and the other things that they saw in the sky. So there's no justification as to why this would be a circle, really, beyond the fact that when you look up, at the sun and you watch its path across the course of the day, it appears to go around us in a circle. And even the moon itself looks like it goes around us in a circle as well. It takes about a month for that to do that. In fact, the origin of the word month, actually, it's month, because it takes about 30 days for the moon to go around the Earth and return back in this model. So that said, if you think about what a circle is, if you take and you draw a line like this through the center, through its central point radius, like this, no matter how you fold one side of a circle over the other side of the circle, as long as the line that you've drawn goes through the center, then the sides always line up. Okay, so that's an example of symmetry. And in circles, we would say perfect symmetry, because no matter how you draw that line, as long as it goes through, it's going to be a symmetric effect. Now, there are plenty of other shapes that exhibit some level of symmetry. A good example of which we'll say would be a rectangle. But the symmetry that you see in a rectangle is limited. For example, if I were to draw a line through the center like this and fold this side over this side, it would line up perfectly. If I were to draw a line through the center of the rectangle like this and fold this side over this side, it would fold over perfectly. But if I took and I drew a line like this through the center and tried to fold this side over this side, there would be overlap. So we would say that a rectangle would be symmetric about these two axes right here, but not about any other axis, really. All right. So again, symmetry was what they considered to be an example of perfection, and circles exhibit this, and yada yada yada. As a consequence, it was a circle. Now, that said, there was a problem in this, and the problem specifically came when you look at the orbits of the planets, quote unquote, around the Earth. Now, what you're looking at here is Mars, and what you see here is something called retrograde motion. So if you look at the bulk motion of Mars, we'll say around the Earth, it goes around thus. But if you look at its behavior as it goes around us, it has these places where it's going around us, going around us, going around us, slows down, and then it actually backtracks. Well, we call that retrograde. Retro is, backwards. So it backtracks like this, slows down, and then continues along its sort of march across the sky. So if you were going to create a model or a cosmology of the universe, okay, and you're going to use circles to do this, when you come across this, there's really no easy way to make a single circle with a planet on it do this. So this is an issue. And it confounded the early Greek for a long time, up until roughly around 200 AD, when you had this guy named Ptolemy. That's this dude right here. Now, so Ptolemy actually came up with this clever idea, which is entirely incorrect, but for all intents and purposes, it'll serve us right now. And even though these models that they're coming up with aren't right, they're still as good as what they could come up with at that point. All right, so you can't hate on them for it, really. So here we'll say there's the Earth at the center, and then here is an orbit of a planet going around the Earth. And so, in order to mimic this type of behavior, what he did was to say that, that the planets actually went around the Earth on circles attached to circles. So this, for example, might be Mars's orbit right here. So this would be the center of this circle right here. And here's Mars right here, we'll say, going around like that. So as the center of the circle traverses its orbit and creates this bulk path right there, You have Mars also going around on its little circle. And as a consequence, it backtracks like that and creates retrograde motion. Now, there's really no other way to describe this as anything other than wrong. I mean, I guess don't let the flat earthers know about this. But this isn't right. But it's a good approximation to what's going on. And it also enabled them to do things like predict the location of Mars in the sky on such and such date. Okay. So in the Ptolemaic model, you're able to do some level of prediction. Now, what I would like to point out here is the ordering of the planets. You have Earth at the center, you have Moon going around the Earth, you have Mercury and Venus that sit between the Earth and the Sun. Now, this is correct, in reverse. But one question you may ask is how do they know that that this was their positions? Well, there's two reasons. So one reason is this: if you look at the amount of time it takes for this retrograde action to happen, okay, for the loop back onto itself and to return to its path, for planets like Mars, Jupiter, and Saturn, it took 1 year. Okay, 1 Earth year. But for planets like Venus and Mercury, it took much less than 1 year. Now, the reason is because, in truth, what you're seeing is the imprint of the Earth's motion around the sun on the orbit. And we're going to talk about that here in a moment. But with Venus and Mercury, since they actually do sit between us and the sun, when you see them perform retrograde motion, what you're actually seeing is their own orbit being imprinted in what you see as you go around the sun. So they correctly sort of deduce that these guys had orbits that were less than a year, so they must be what you would sort of perceive of as inferior planets to sit between us and the sun. But also, if you look at the size of the loop, okay, and you think about perspective, you're sort of left with the conclusion that these must be there. Now, you also have the fact of transits. Now, under the right circumstances, we'll say with a lot of fog, or if there's smoke in the sky, if it gets between us and the sun, you can safely observe the sun with your eyes. Now, don't look at the sun without some sort of protection for your eyes, and definitely don't do it through a telescope unless that telescope is designed for it. That said, Mercury and Venus, since they sit between us and the sun, will actually transit across the surface of the sun as shadows. So not literally the surface, just the disk that we see. So this is called a transit, and these are the only two planets that do it, and these don't. So all the information that they had led up to the fact that Mercury and Venus sit between us and the sun. Mars, Jupiter, and Saturn, they sit beyond, and that was it. They didn't know about. You'll notice here that planets like Uranus, Neptune, and even my favorite underdog, Pluto, here. You don't see these here, and that's because they didn't know about them. These are so far away that in order to see them, you need some sort of assistance for the eyes. You need a telescope. You need a good telescope. And at this point in time, telescopes don't exist, so they haven't been created yet. Now, the Ptolemaic model was the de facto model for the universe from about 200 AD to about 1600 AD. Okay. And the reason why, in part, was because of the church. Roughly around 200 AD, you had Christianity take hold in a huge way, spreading out specifically from Rome, outwards. And one of the ways it did that was through conquest. And the church itself, because it was the official religion of Rome at the time, had a tremendous military presence. And basically anything that went against the teachings of the church would be considered to be heresy, and would end up with you being You would hope swiftly executed, but generally there's a lot of torture involved before that happened. So, so even though people may have had ideas about this being wrong, they didn't speak out because they didn't want to get killed. Now, that said, obviously this is not how we think now. Things have changed. So what happened? Well, it started with this guy right here. This is roughly in the year 1400. Okay, and this guy right here is Nicholas Copernicus. That's not his real name. Nicholas Copernicus was a medical doctor, and it turns out that doctors back then, when they would graduate from school, they would typically assume some very official sounding name in Latin or in Greek or something like that. And that was to give them prestige and to demonstrate that they had graduated from medical school, and that's what they would typically be called, from henceforth. And that's exactly what he did. He also was an astronomer and an astrologer. They considered back then astrology to be legitimate science. It's nonsense, obviously, but nonetheless, that's how it was back then. And Copernicus was incredibly well read. And by 1400 AD, if you think about the Ptolemaic model being created around 200, this is 1200 years, and in 1200 years, you saw advancements in observational techniques. You saw, higher and higher quality data. Still, no telescopes being used in the West in astronomy. They did exist, however, in the Middle East. Okay, the Middle East actually had a fully developed theory of optics well before the West did. So that said, Copernicus is very well read, like I said, and he had read some works that referenced a astronomer from ancient Greek times named Aristarchus of Samos. Okay, now so Aristarchus lived, I'd say, roughly around 300-ish BC, and he had actually written about the idea that maybe the sun sat at the center and everything went around the sun. Now, his idea didn't win out. This, if you were to do that, then everything that you saw on Earth would be an issue of perspective. And like I said, the Greek believed in a literal view of the cosmos, basically. But the issue is by now, what they're discovering is that because of the quality of their data, if they take their data and they put it in the Ptolemaic model, higher quality data doesn't give you a higher quality prediction. The predictions are still sort of nonsense, and there are a lot of correction factors they have to add into the model in order to get right answers and stuff like that. So it's becoming more and more obvious that there's something going on with the Ptolemaic model, and so Copernicus says, I wonder what it would look like in Aristarchus's universe. So you put the sun at the center, and then basically you use the idea of perspective, what we see here from the Earth, and the fact that as the Earth goes around the sun, its orbit would be imprinted on the motions of the planets. Okay, to deduce not only the distance from the sun, but also the ordering that you would need in order to make this work. Now, he did not know how far away the Earth is from the sun. He did give it a number. He said, okay, we're going to call that distance 1. The idea being is that if you get an exact measurement of what that is, then you can just take and fill that in for 1, and now your model works. So we call this 1 astronomical unit. And it actually is the scale that we use to fit the solar system, and is typically an AU. And that's because it fits it well, kind of like miles, fit, distances that are terrestrial between cities. Here, astronomical units fit distances between planets. So this is sort of like the astronomy equivalent of the mile. All right. Now, that said, you'll notice the ordering here: Mercury, Venus, the Earth, the moon goes around the Earth, then you have Mars, Jupiter, and Saturn. And this is absolutely correct. Now, if you look here, though, you'll see that when it came to deducing the distances of the planets from the sun in units of Earth to sun distances, he was very close to modern values. So Mercury, according to him, was 0.38 times the distance the Earth is away from the Sun. The modern value is 0.39. Venus, he got dead on. Earth is defined to be this. Mars, he got dead on. Jupiter, he got really close. I mean, this is more or less dead on. Saturn's a little off, but that's because Saturn's so far away that it takes a tremendous amount of time for it to go around the Sun once. Okay. And so high quality data on that's a little bit harder to produce. Now, that said, let me talk about how this also handles this issue right here, the issue of retrograde motion. So, so to do that, I want you to again imagine that you have, the sun, we'll say, at the center of our cosmology now, which is getting closer and closer to being correct. All right, and then we'll say, here's the path of the Earth. I probably should have done that. Let me put it over here, and I'll put it here like this. So here's the Earth going around the sun like that. And then what I'm going to do is I'm going to put Mars's orbit way out over here. So here's Mars's orbit like this. It's really far out. And again, I'll tell you what, let me do it this way. Let me add another slide. And I'll draw it here, just so I have plenty of space. I can cut it and paste it. All right. So here's Mars's orbit, like this. And next, what I'm going to do is I'm going to put a bunch of background stars. So here's stars very far away from us. So here are the stars very far away. Now, why stars? Well, look, when I watch this behavior of Mars over the course of several months, I'm seeing it relative to what we would think of as fixed background stars. Now, these things are continuously moving, but they're so far away that their motion is imperceptible to us unless we use a telescope and we observe these things for several years. So, for all intents and purposes, especially in the time scale of an orbit, these things remain fixed. So, what I would like to do is to place Mars, we'll say here, and we're going to let Mars hang around in its orbit right there. So, we're going to pretend it's fixed. And I'm going to take and place Earth in its orbit in a couple places here. Like this. So these are just different places I've picked in the Earth's orbit as we'll say it goes around the sun like this. So we'll say it's going around like that. Now, so look. Here I am on Earth right here. And I look at Mars. And when I look at Mars, I see these stars behind it because that's in the line of sight. Now, as the Earth continues to go around Mars, like this, not around Mars, but around the sun. What I'd like to point out is that when I continue to look at Mars, the background stars that I see are further and further and further this way. And what that means is that Mars, according to my field of view, looks like it's moving this way. Now, as I continue to go around the sun, you can see how it continues this way. But look, as I get closer and closer to the cusp of my orbit here, it slows down. And then when I finally pass the cusp and I end up going this way, and I go this way, you see how now I'm going down? Now it's going the other way. So what happens is this. As the Earth goes around the sun, what you see is the Earth's motion around the sun imprinted on what we see in the sky when we look at Mars. So you see it appear to slowly go this way, and it speeds up, and then it's going to slow down, and then it's going to look like it goes back the other way. Now, if you add in its own orbit around the sun, you end up with this type of motion right there. So that's your retrograde loop. So there's no need to do like what Ptolemy did and to add these circles upon circles in order to make it work. In reality, if you just take and you put the sun at the center and you let everything orbit that, with the exception obviously of the moon, then you're golden. Now the issue that you have here though is that instead of placing the Earth at the center, which is incredibly attractive, not just from a literal view of the cosmos perspective, but also from a religious standpoint. I mean, the Earth is special, man is created in God's image, that sort of stuff. So it must be at the center. Now what you've done is sort of demystify the Earth's place in the cosmos by making it just another planet that goes around the sun. And if you're Nicholas Copernicus, who is a smart guy, you realize that if you were to publish this, the church would come and get you and vanish you. And so he doesn't publish it. He waits on it, sits on it. And he has a friend who owns a printing company, and he talks to his friend. His friend says, look, you and I both know that there will be a time in which you are no longer on this planet. So what I would like you to do is to write your article up, write your paper up, your book, if you will, describing this. And when you die, I will have it posthumously published in your name. So the worst thing the church can do is to show up looking for you, and people will be like, well, I mean, he's dead. So that circumvents, you being tortured. And he said, yeah. So that's exactly what happened. Copernicus passed away, and eventually his book was published. And, the church condemned it as being heresy because, by their standards it was. And but the thing is that the worst thing you can do to knowledgeable people is to tell them not to read something. And so the act of condemning this thing as being nonsense and saying, things like only a fool would believe this view, basically meant that every astronomer read it. And it convinced many, many of them. So that took roughly about 150 years. And then we get to this guy right here. Actually, two people, this guy right here and this guy right here. So this right here, this is Tycho Brahe. We have a year. This is in 1600. And Tycho, other than having this amazing mustache, was an aristocrat, very, very wealthy. He was, I'd say top 3 best observational astronomers that ever lived. Incredibly good at this. He built his own observatory. He used a good bit of his money and built this cutting edge, which at the time was the most advanced scientific thing ever created. And he made very, very, very high quality observations of planets and of things. Now he did a number of things that helped sort of buck against the still existing view of the Earth being at the center. The church is still pushing the idea that the Earth is at the center. Okay, so one of the things he did was to observe the behavior of a comet in the sky. It was believed previously that comets were these luminous vapors that sat in the Earth's upper atmosphere. And the reason why was because one of the sort of footholds of this thinking that had been going on at the time is that anything up in the sky is permanent and unchanging. Well, comets change continuously, in their approach towards the sun and as they leave. So what he did was to do parallax, which is a trick of estimating distances based off of perspective and stuff. And he demonstrated that that comet actually was out amongst the planets, which is a huge deal. Tycho actually also observed a supernova, which is an exploding star, and he called it a new star, which was a big deal because it demonstrated that the stars themselves can change. But his data was so good that today we have been able to go back and look at the location of this guy and find the same thing that he was looking at. I mean, that's how good of an astronomer this guy was. He was also a genius, um, but he wasn't a very good mathematician. Now, he had read the works of Copernicus, and he agreed with but disagreed with Copernicus in that he believed that Copernicus was kind of right in that the planets went around the sun, but he still believed that the sun went around the earth. Now, if you look at this model over here, which is called the Taconic model, this is an absolute nightmare. I mean, you don't want to work in this, but he doesn't. He still needs to sort of verify that this is or isn't correct, and he needs a mathematician to do that. And that's where this guy comes in. So this guy is Johannes Kepler. And Johannes Kepler is a school teacher. He's a mathematician, an incredibly skilled mathematician, by the way. He's a genius. And he has his own model. So he's read the works of Copernicus. He thinks Copernicus is, again, right about, the sun being at the center. And he thinks that the planets do, in fact, go around the sun. What he disagrees with Copernicus about is the shapes of the orbits. Now, look, if you look here, Copernicus has chosen circles. Why did he choose circles? Well, for exactly the same reason that the ancient Greek did circles. They must be. No real justification other than the fact that they must be. Now, so Kepler disagrees that the shapes are circles because in Kepler's mind, those aren't perfect enough. Any creator worth its salt in creation, if you will, would choose these things right here. These things are called the Platonic solids. Now, Platonic solids are shapes in which all the sides are the same, and the sides themselves have lengths that are the same and angles that are the same. So, for example, a cube or a pyramid or all these other shapes that we have basically looks like Dungeons and Dragons dice. These are all Platonic solids, okay? And as such, he views these as being even more perfect than circles. So why would a creator not use them? And he built a physical model to try to demonstrate this. As you can see, you have all these Platonic solids sitting in here, and they would basically form the boundaries of the orbits that the planets went around. Now, what Kepler is missing here is data. He doesn't have data. And he's not working as an astronomer. He's working as a school teacher. He just doesn't have access to it. So what happens is in the year 1600, which is the reason why this is a solid date, Tycho, is reading these journals and he keeps coming across the works of Kepler, and he's just more and more impressed by him. And he sends a letter to Kepler and says, "Hey, come work for me." Okay. Kepler gets this letter and is like, "Yes, this is fantastic because now I can get data. And not only do I get data from, one of the top 3 best observational astronomers who's ever lived. I mean, this is perfect." But not quite. And here's why. So Tycho is a genius. And aristocrats in general are idiots. Okay. For those of you that know anything about, the aristocratic position or class back then, they were heavily inbred. They weren't very smart, very herf derf. And he had a hard time finding anybody in the aristocratic realm that was worth talking to. They're all idiots. So what he would do is when he met somebody who was brilliant, who he had interesting conversation with, he would invite them to come live with him. He would be their patron. And his expectation was that if he stopped by and wanted to have a conversation, you would get the conversation. So he collected people. Now, Kepler was easily as, or even more, smarter than Brahe. And when Brahe came and invited, Kepler to come live with him, when he showed up, he realized that. Okay, and so there was tension. There was tension not because Kepler was smart, but because Kepler offered potential competition when it came to science. So Tycho actually would during like their these extravagant dinners would pass 2 or 3 data points to Kepler and say, "Hey, look at what I did," but would never actually give him direct access to the data. Now that was true up until about the year 1601, and in 1601 Tycho died. Okay, now to be clear, they didn't hate each other to the point that Tycho on his deathbed actually said Kepler was the one who was going to assume his position. Now, Tycho was the royal astronomer at the time, which is an incredibly prestigious position. And he gave it to Kepler because he felt Kepler was the right person to assume it. So obviously, there was a lot of respect there. It was just, for whatever reason, the ego between Brahe, well, primarily Brahe's ego, just did not allow him to compete. But I mean, Brahe's dead now. So Kepler now has the same position as Brahe did, and he knows how to use all the tools, and he's got all the data. And the first thing he does is to take that data and to plug it into his model, and he realizes that this is garbage. If you, for example, were to look at the orbit of the sun across the sky and try to fit a platonic solid to that orbit with the sun at the center, it doesn't work. Okay, it's terrible. It's a terrible fit. So, knowing this, Kepler says, all right, well, I still think the sun's at the center. And, Copernicus, when he originally did his work, he used circles because circles were perfect shapes. So, what I'm going to do is I'm going to fit a circle as well. Now, so he takes data basically of Martian observations, his observations of Mars that Brahe had done. Brahe, for whatever reason, just was fascinated with Mars and had really, really high quality data of Martian observation. And so he fits a circle to it. And what he discovers is that the circle is a very good fit, but it's not a perfect fit. Well, in his mind, that exhausts basically the extent of perfect shapes. And the circle is the best, but it's not exact. So he says, okay, well, why don't I just fully parameterize the circle? Now, a fully parameterized circle is an ellipse. So this is an ellipse right here. Now, you have 2 axes here. You have what's called the major axis, and then you have something called the minor axis. It's these axes right here. When the minor axis and the major axis are of the same length, you have a circle. Now, this right here, half of the major axis, is called the semi-major axis. For a circle, this would be a radius. Now, at the ends, close to the ends, along the major axis, equal distances from the ends, you have 2 points that are called a focus or focal point, or you can wrote from a plural standpoint, they're called foci. All right. So in calculus, you typically see these things evoked in Calc 3. because that's where you see vector calculus in great detail, and that's where you deal with complicated curves and stuff like that. Now, the thing is that in 1600, Newton has not entered the scene yet, and as a consequence, there is no calculus. There is no physics at this point. So here's what happened. Kepler took this ellipse and parameterized it and fit it to Mars's orbit, and it was a perfect fit. So at this point, Kepler could have easily have said, well, the data isn't good enough. I still think it's a circle. It's probably still circles. Now, that would be a view influenced by his religious belief. But no, he took the good scientist approach. He said, well, you know, it's not a perfect shape. The orbits are not perfect. All these assumptions that we've made for like the last 1,400 years or longer, actually, they were wrong. The orbit is not a circle. It's an ellipse. And if it's an ellipse, I mean, God's the one who created it. It can be whatever shape he wants. And you got to admit, for somebody who worked with a model like this for years, and then was presented with data to fire his model out of a window, basically, and say, well, this is what it is, that's the act of a good scientist. Now, that said, over the course of about 10 years, Kepler continued to work with data, and he came up with 3 laws. We call them Kepler's laws. Now, Kepler's laws are what we call empirical laws. Now, so there are 2 basic types of laws. You have empirical laws, which are laws based off of what the data says. And then you have theoretical laws, which are laws that make some sort of profound statement about nature or something like that. So these are empirical laws. He's just looking at data. Nonetheless, we still use them today. And the first one is this. Planets orbit the sun on ellipses with the sun at a focus. So let me snag this ellipse right here. Oh, got most of it, I guess. I just clean it up. There. So what I'm going to do is to put the sun over here. This would be where one of the focal points is. It doesn't matter which one. If you put it here and you have the planet go around like this, that's the same thing as putting the sun here and having the planet go around the other way. It's all an issue of whether you're looking at it from the top or looking at it from the bottom. So you take and you put your planet on the ellipse that you fit to its orbit, and the proper place for the sun is at one of the focal points, and the ellipse is the path that the planet takes around the sun. So that's what this says, basically, is it tells you, once you parameterize your ellipse, where the planet sits and where the sun sits. Now, let's talk about the second law. The second law says this. A line drawn from the sun to a planet sweeps out equal areas in equal times. So here's my line. Now, let's pretend, just for the moment, that this planet goes around the sun in 10 years. So I look 1 year into the future, and maybe that planet's here. Now, over the course of that year, this line swept out this area right here. So this is an area right here. All right. Now, this area is formed by this side right here, which is where the planet is now, this side right here, which is where the planet was, and this length of the ellipse right here. So let's pretend that I look 1 year into the future. So 1 year into the future maybe puts the planet right here. So if you notice, as this planet gets closer and closer to the sun, the length of r, the distance from the center of the sun to where the planet is, gets less. As a consequence, in order to get the same amount of area, you have to capture more of the ellipse. So this part of the ellipse right here would be longer than this part of the ellipse right here, but it was done in the same amount of time. So if I call this 1 and I call this 2, and this distance right here, I'm going to call an arc S1, its length, and this is S2. My speed on average along the first path would be S1 over 1 year. Along the second path, it would be S2 over 1 year. And here's the thing though, S2 is longer than S1, which means here, this is faster. In fact, at its closest approach right here, you would discover that the planet itself would be going its fastest in its orbit. And at its furthest approach right here, this would be at its slowest in the orbit. Now, believe it or not, we already know about this. Case in point, last chapter, L is equal to R cross P. This is R. This is P. It's conserved. Your angular momentum in this situation is conserved because there are no external forces acting on these things. So what's happening is this. As R gets smaller, for L to stay constant, as R goes down, P goes up to make this stay constant. So when R is at its smallest, P is going to be at its greatest, which means your velocity is going to be at its greatest. And when R is at its longest, P is going to be at its least, which means that your velocity is going to be at its smallest. So what Kepler has actually discovered in his second law is conservation of angular momentum. But he doesn't know it, and the reason why he doesn't know it is because angular momentum at this point in time doesn't exist as a concept. So it's not there, at least conceptually. So, the last law is this. The period of a planet's orbit around the sun squared is proportional to the length of the orbit's semi-major axis cubed. So we're going to use capital T for period and R for semi-major axis. T squared is proportional to R cubed. Okay. Now, the question here is, what's the constant of proportionality? And there are a number of different ways in which you could calculate this. The one I'm going to initially use, and later on we'll come up with a more complicated one, is based off of stuff that we know right now, specifically the orbit of the Earth around the sun. The period of the Earth's orbit around the sun is 1 year. It spins, according to Copernicus, 1 AU as a distance away from the sun as it goes around. So, if you write Kepler's third law this way, and you solve for k, and you plug in a specific case that you know about, the Earth. This would be the constant of proportionality. Now, so here's the thing. All three of these laws, um, the shape of the orbits around the sun, conservation of angular momentum, or the second law, plus the third law, these laws all work incredibly well for the orbits of the planets around the sun. Now, a little bit of time after these laws were published, you had Galileo Galilei pop up. Now, Galileo was the first one to apply telescopes to the sky. He did not invent the telescope, okay? He had a friend who saw a telescope that had been created. Actually, it's a spyglass that had been created somewhere up in the Netherlands. And had sort of thought to himself, Galileo would really enjoy this. And so he wrote up a description as to how the telescope was created, sent the letter to Galileo, and as a consequence, Galileo actually ground his own lenses and made his own telescope. One of the things he discovered roughly around 1650 or so was that planets like Jupiter have moons. And if you look at the behavior of the moons as they go around Jupiter, they orbit on ellipses with Jupiter at a focus. A line drawn from Jupiter to a moon sweeps out equal areas in equal times. And the periods of their orbits are proportional to the lengths of the semi-major axes of their orbits. The difference, though, is the constant of proportionality. Now, believe it or not, Kepler suggested, or had a sneaking suspicion, rather, that hidden inside this constant of proportionality was mass. That is, the mass of the thing that's being gone around. But he couldn't justify its existence there. And he had actually tried to come up with an analytical fit that he wasn't able to successfully get before he died. So he knew, or at least suspected, that mass was hiding around in here. This right here, when you think about the orbits of the planets versus the orbits of moons, also suggests that the thing that you're orbiting around matters. Now, the person who was able to rectify all this is somebody we've already talked about already, and that's Isaac Newton. Remember, one of the things that Newton was known for was coming up with a working theory of gravity. It's called the law of universal gravitation. Now, it looks like this. If you think of two objects experiencing gravity, we'll say the distance between them is r. This object has one mass, this object has another mass. The force felt between them looks like this. Now, this equation is a little bit different than the one that's in your book. And the reason why it's different is because your book leaves off the negative sign and I think uses arguments to justify attraction. Gravity, as best as we can tell, is always an attractive force, at least the one that we know of right now. There's some suspicion that maybe, they're under certain circumstances it can repel, but we're not entirely sure about that yet. So it's an attractive force, which is the reason why there's a negative sign here. So it's always attractive. Plus, it's a central force. And by that, it causes centripetal acceleration. All right. Now, this G here is the gravitational constant, and it has a value of, right here, 6.67430 times 10 to the minus 11th Newton meters squared per kilogram squared. All right. Now, there's an experiment called the Cavendish experiment that was used to actually determine this value very accurately. Subsequently, we've made even more accurate measurements of it, and it's about this. Now, this is what we're going to start talking about in our second video. Okay. How this was deduced and how we use it. And I'll see you then.